this video specifically keeps practicing with the application of the properties of the definite integral. If you want to see how to evaluate a definite integral from scratch, we can either evaluate that definite integral from its limit definition or from what's called the fundamental theorem of calculus. Those two topics are topics of another video. Here we're going to just revisit our properties of definite integrals. We're going to be given some specific definite integral values and then answer associated definite integral questions that we can utilize our properties and or our values that were given in that particular question. So when you're doing problem types like this, make sure you carefully read what the directions say so you know what it is that you have as given information to use within answering the question. And also make sure you write out what you're doing by the using of your properties to make sure that you present that you know what the properties are and how to utilize them. So just as a recap, and in a video that I'll link in this description, I've gone a little bit more in depth as what it is that our background requirements that you need for these definite integral properties to be true. But for now, we're just going to go through and just review them quickly. So if you have an integrable function over an interval and your definite integral is from the lower limit of integration of a to the upper limit of integration also a. So the lower limit and the upper limit are the same numerical value as each other, then your definite integral of f of x dx, whatever it is going to come out to be 0. Okay, so always look at those endpoints of integration. If they match, then your definite integral value is going to be 0. Also, we have that the definite integral from b to a of f of x dx will be the opposite in sign of the definite integral from a to b of f of x dx. So if we switch the limits of integration, what was the lower limit of integration is now the upper one, and what was the upper one is now the lower one. It changes the sign of the definite integral answer. Next up, if I have some value in my closed interval that's represented by the lower limit of integration and the upper limit of integration of my definite integral, for that value somewhere in that closed interval, I can take the definite integral from the start of your interval to that number f of x dx plus pick up at that number and go to the rest of the way off to the end f of x dx. So your intervals are additive. You can take your definite integral from a to c and then add to it the definite integral from c to be equivalent to the overall definite integral from a to b. And that's what that is telling us. The next one is telling us that if I have a constant factor, a constant multiple to my function in my integrand for my definite integral, I can bring the constant factor out and multiply it to the answer I get for my definite integral. Next up is the definite integral of f of x plus or minus g of x dx. I can do term by term definite integrals just like I did term by term indefinite integrals. So remember, that means that you can look at the definite integral from a to b of f of x dx as a separate problem, and the definite integral from a to b of g of x dx as a separate problem. Get those answers and do what other operation of addition or subtraction that was originally in between those two functions, in between your answers of your individual definite integrals. Now, don't get too crazy with this and go to other operations. This does not work for the multiplication of two functions, and it does not work for the division of two functions. But it does work for the addition or subtraction of two functions. So we can do term by term definite integrals. Now these last three are really handy if you're really watching out what you have and you notice it, then it's helpful. So this one will really help so that you don't have to do cumbersome calculations sometimes. So if your function f of x is an even function, remember an even function is a function that's symmetric with respect to the y-axis. So if you have a function that's symmetric with respect to the y-axis as your integrand. And your lower limit of integration is the opposite in sign of your upper limit of integration, so it's equally spaced over the origin, then that definite integral can be found by taking 2 times the definite integral from 0 to a of f of x dx. Next up, if f of x is an odd function, so odd function, remember, is symmetric with respect to the origin, then the definite integral from opposite of a to a of an odd function is going to be equal to 0. And then if your f of x is greater than or equal to 0, if it's on the x-axis or above throughout the closed interval that you're integrating over, then your definite integral from a to b of f of x dx is actually the area of the region enclosed by your function, the x-axis, and the vertical lines at x equal a and x equal b. So when my function is above the x-axis, or could touch the x-axis, over an interval, then my definite integral will actually be the area of that region. Now, if you remember back, when we were asked to find the area of an enclosed region like that in a previous work that we did, we had the limit definition that we did for that. And so that involved a lot of summations and limits as n approached infinity and all that sort of thing. So this is a great help when I have my function non-negative over the interval. And actually, it'll be a great help when we see other scenarios and how we might be able to adjust them to get areas of regions as we go out. So that's a recap of our properties of definite integrals, and I want to use that recap to answer these questions. So the setup is telling me that the definite integral from 0 to 3 of x squared dx, that value is equal to 9. Again, later we will find ways that we'll just figure out what the definite integral from 0 to 3 of x squared dx is by our other work. But that's not the focus of this video. The focus of this video is our properties. So I'm telling you that that's equal to 9. And then also the definite integral from 0 to pi over 2 of cosine x dx. That value is equal to 1. Now my part A is, what's the definite integral from 2 to 2 of x squared dx? Well, it's x squared dx, but this is 2 and 2, and it's not the values that I have in the setup. But it's 2 and 2. The lower limit of integration matches the upper limit of integration. So that is this property, that definite integral value is 0. So that one just comes out to be 0. Next up, part B. This is the definite integral from 3 to 0 of 4x squared dx. This one's actually going to take a couple properties to get the answer. One of the first properties is that I can notice that this 4 is multiplied to the x squared in the integrand, and I have this property that if I have a constant multiplied to my function, I can bring the constant factor out. So this is the same as 4 times the definite integral from 3 to 0 of x squared dx. And then I look at my setup, and this is the definite integral from 0 to 3 of x squared dx, and in my problem I have the definite integral from 3 to 0 of x squared dx. So the numbers match, they're just in the wrong order of the lower limit of integration and the upper limit of integration, and that's what this property is for. This will help me rewrite it so that I have the end points of lower limit and my upper limit of my integration to be what I need it to be to match up. So this will be 4 times the opposite in sign of the definite integral from 0 to 3 of x squared dx. Then the definite integral from 0 to 3 of x squared dx is 9. So then that's 4 times negative 9, which gives me a negative 36 for that definite integral. And I want to write out the properties so that I show that I am using the properties and using them correctly in order to find my value. Okay, next up, part C. This is the definite integral from -3 to 3 of x squared dx. Well, I've got the x squared dx, but this is -3 to 3, and that's 0 to 3. X squared, if you think about this function x squared, I'll just kind of sketch it out here. My function x squared, well, that's a parabola opening up with a vertex at the origin. And over the span from -3 to 3, I'm left as much as I am right on my interval. And this function is symmetric with respect to the y-axis. My y equal x squared is an even function. So my definite integral from -3 to 3 of x squared dx, since x squared is an even function and these are equally spaced around the origin, is going to be 2 times the definite integral from 0 to 3 of x squared dx. But the definite integral from 0 to 3 of x squared dx is one that they gave me. That's 9. So this is 2 times 9, which gives me a value of 18. So this requires you to kind of pay attention to the functions that you're integrating and what you have for your lower limit and upper limit of integration. So if I ever have my lower limit and my upper limit of integration being opposite in sign of each other, I really look at that integrand to see, hey, is this an even or an odd function? Because if so, then I can make my life a little bit easier in working out that problem. Next up, D. Again, look, I have opposites on my lower limit of integration and my upper limit of integration. And then when I think about sine x, well, y equals sine x is symmetric with respect to the origin. Y equals sine x is an odd function. And if I have my function, that's my integrand, is an odd function, and I'm integrating from the opposite of a to a of an odd function, my definite integral is just going to come out 0. So saved me a lot of work, especially because we're not at the point in this process where we're actually figuring out the definite integral value from either the limit notation, limit definition, or from the fundamental theorem of calculus. We're only working with the properties and some given things that we are presented in the problems that we're working. Okay, and then last up, I have my definite integral from -pi/2 to pi/2. Okay, I've got those opposites on my endpoints of integration. It's not always going to be the case that it's an even or odd function, but a lot of times it might be. And so here it's of cosine x dx. And remember, cosine x is an even function. So y equal cosine x is an even function. So that is going to be 2 times the definite integral from 0 to pi/2 of cosine x dx. But the definite integral from 0 to pi/2 of cosine x dx is just 1. So this is 2 times 1, or 2. So hopefully just having even more of the different examples of the properties of definite integrals and how you can use them is helpful. I'll link the video, like I said, of the earlier one that I did to this one so that you can see it if you want to get a more in-depth description of the properties of definite integrals. And otherwise, thank you for watching my video, and I hope you have found it helpful.